Okay, so this is from 2019. It's number 3. The situation is we have this launcher that's operated by a spring inside of it, and the spring can be compressed 3 different distances and held there with a pin. So we got, C, B, A, with A being the farthest compression. And the hypothesis made by this student is that the spring constant of the spring has the same value for different compression distances. So regardless of whether we take this plate here and compress the spring to C, or whether we take the plate and compress to B or compress to A, regardless of how far we compress the spring before launching this sphere, the spring constant stays the same. And you know what? Let's just real quick, let's review spring constant in case you forgot that. So spring constant, every spring has one. It's unique to a given spring. The fundamental equation for force of spring is the constant times how far the spring was compressed or stretched. So for example, look, you got a spring right here. Let's say that this spring has a spring constant of 50 Newton per meter, which is the unit, right? If you take this, K is going to be force of spring over X, which gives us units of Newton per meter. So let's say we grab this spring and let's say we stretch it 1 meter. So the spring would be exerting a force back, force of spring. Well, what would that force be? Well, it says 50 newtons per meter. So we plug into this, we're like, K is 50, X was 1. That's going to be 50 newtons. Well, what if we would have stretched this 2 meters? So now the force of spring is going to be bigger, right? Because the constant is still 50 newtons per meter, but now we've stretched it 2. So that gives us a force of spring now of 100. Now, the other equation for that involves spring constant is energy in a spring. If you grab a spring and you stretch it, there's going to be energy stored in that spring, and we call that potential of spring, where U represents potential energy, and the equation for that is 1/2 K, which is the same K as up here, X squared. And again, X is how far you stretch or compress the spring. All right, so we have multiple options for this again. There's not just one possible answer to this. So I'm going to go through a few different options. Now for A is this first question is pretty straightforward. The student plans to test the hypothesis by launching the sphere using the launcher. So 1, state a basic physics principle or law that the student could use in designing an experiment. So this is going to be conservation of mechanical energy. So if this is your launcher and here's the spring, so here's the spring and it has not been compressed yet, so the ball is right here. If you take this and you compress it back a distance X, before launching, you're going to have potential energy of spring and no kinetic because it's nothing's moving. When you release the launcher, this ball is going to come flying out of the launcher with kinetic energy. No more potential of spring because the spring is fully relaxed now. So we start with potential of spring, we end with kinetic, as long as we can assume that there's no friction inside the launcher. In fact, did they mention that? I don't think they mentioned it. They didn't mention it, but the rule is if friction is not mentioned, you can assume it's frictionless. So friction was not mentioned, so this is a frictionless launcher. So this is the answer number 1. So the physics principle is conservation of energy. Now, part two, using the principle or law stated in the first question, determine an expression for the spring constant K in terms of the quantities that can be obtained from measurements made with equipment usually found in school lab. All right, so we're on our way to the answer right here. So we're doing this one here. So our equation's going to be, well, potential of spring, which is the energy we start with before launching. That's 1/2 kx squared. The equation for kinetic energy is 1/2 mv squared. My tablet's acting funny. Okay, we're back. Okay, so that should be a squared right there. Okay, so the 1/2s cancel out, and we're solving for K. K is going to be mv squared over x squared. And this is all measurable. So in a moment, we're going to be talking about measuring the mass of the sphere. We're going to be measuring the velocity of the sphere as it shoots out of the launcher. And then X is how far the spring was compressed before launching. So all of those are measurable. So now we're done with A. So now we're on to part B.
Mr. Spalding?
Yeah.
For A, is it okay for if you used Hooke's law? Force equals K times X.
Well, but they specify here that they want the ball to be launched. So I don't know how, I can't think of how we would use Hooke's law with launching the ball.
Because you could make force into mass times acceleration and then make like mass times change of velocity over time.
Well, let's do this. I'm recording this video to post. Let's do that at the end.
Okay.
So we don't go down a rabbit hole. But my thought is, so it's the student plans to test the hypothesis by launching the sphere. And the other thing is, as this spring, so the spring starts out compressed, as the spring accelerates the sphere, right? So here's the sphere inside the launcher. So there is force of spring, but realize that force is not constant. So then you'd have to be like using the average force, right?
Oh, okay.
Use the average. Here force is a maximum. Here force is 0. The average force would just be the initial force divided by 2. But you'd have to get a force sensor inside that launcher to measure the force.
Okay.
Okay, so let's go on to part B. Now, part B, oh my gosh, there's multiple ways that you could do this. So I'm gonna start with option 1, which I think is the most straightforward, and then quickly I'll go over 2 other options that you would have gotten full credit for. So part B, they want us to design an experimental procedure to test the hypothesis in which the student uses the launcher to actually launch the sphere. And then we have basically all equipment available in a physics classroom. Okay, so first thing, we're going to list the quantities to be measured, and then the symbol for the quantity, and the equipment for measurement. So I'm going to begin with a diagram. Before we do this, I'm going to give you the diagram. So what I would do so we're going to call this option number 1. So here's the launcher. There's the spring. And this all takes place on like a tabletop, right? So like here's your table. And what we're going to do is we're going to put a photo gate, which you guys are familiar with. We did labs. The photo gate, I'm a horrible artist, but the photo gate is basically, it looks like I don't know, like a field goal post, looks like that. And then the ball would go shooting through there when it comes out. So this is called a photo gate. or you could just call it a motion. You could call it a motion detector. Okay, so the quantities that we're going to measure. So we would want to measure. I'm just going to fill it in here. We're going to want to measure the mass. The symbol for the quantity is m, and we're going to use a balance. You could say electronic balance. We need to measure the distance. The spring is compressed. We got to measure how far the spring is compressed. The symbol we're using for that is x, right? How far was the spring inside the launcher compressed? And we could just use a ruler for that. If you said meter stick, I mean, the difference between a ruler and a meter stick, a meter stick is much larger, but you would still get credit for saying meter stick, because perhaps your physics classroom only uses meter sticks, which in fact, I think that's I don't think I give kids rulers. We just use meter sticks. All right, we would also need to measure the velocity of the sphere as it exits the launcher. And then that's just going to be V, and we could use, you could say motion detector, or you could call it a photo gate. Either one is fine. All right, so that would get you full credit for part B. Part B, we just nailed it. Okay, the second part of B. Describe the overall procedure to be used to test the hypothesis that the spring constant of the spring has the same value for different compressions. And we need a lot of detail. And we want to reduce experimental uncertainty. And the way you're going to do that is by having multiple trials. Okay, so our procedure for this is going to go like this. So I'm just going to say it out loud, and if you want, you can copy it down. But I did this in 6 steps. So first step, I wrote, measure the mass of the sphere. Measure mass of sphere. Second step, place the sphere in the horizontal launcher. Place sphere in the horizontal launcher. Number 3, record how far the spring was compressed. Record how far, oh wait, sorry, I left off part of 2. So 2 was place the sphere in the horizontal launcher and compress spring to position A inside launcher. So place sphere inside the launcher and compress to point A inside launcher. So we're going to compress the spring all the way back to point A. And then step 3 is record how far the spring was compressed. Record that value X. Step 4, launch the sphere and record the velocity of the sphere as it leaves the launcher. So the sphere is going to get launched. It's going to come shooting out with a velocity V, like right here. It goes through that motion detector. The motion detector is going to give you the velocity of the sphere as it leaves the launcher. And then you could specify use motion detector placed at the end of the launcher. All right, step 5. We're on to step 5 here. You want to say repeat steps 2 through 4. You don't have to repeat step 1 because step 1 was measure the mass of the sphere. So repeat steps 2 through 4, and the reason why we're doing that is to minimize experimental error. And then step 6 is going to be, and this is very important, repeat steps 2 through 5. Repeat steps 2 through 5 with spring being compressed to position B and then position C. Because the whole thing with this problem is we're trying to figure out if the spring constant changes with how far we compress the spring. So we first compress to A, collect all our data, get the velocity and all that. Then we're going to compress to B, and do that multiple times. And then lastly, we're going to compress to C, to see if these different compression distances affect K. All right, so that is the procedure. So that is really good for part B. So you know what? I'm going to come back to the other options because I want to skip to, I want to go to, this is already a long solution. So let's go to the next part. Okay, part C. Part C is describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. So how could we confirm this? So the equation that we derived previously, I'm just going to derive it again real quick. So spring, here's the sphere, right? We compressed back X. At this point right there, the energy is all potential of spring. We release it. It comes out in kinetic. Assuming no friction, they're equal. So we have this equation of 1/2 kx squared equals 1/2 mv squared. 1/2s drop out. The spring constant should be equal to m times v squared over x squared. So this is what we're working with. So what I would do to confirm whether or not the spring constant remains constant for different compressions, make a data table like this. Make a data table. So position, so they gave us 3 positions, A, B, C, I think it was. So let's go A, B, C. I need to scoot this down. Okay, so the next column, we're going to use the average compression. So line above a variable, that indicates average. Remember, we did this multiple times, right? We compressed the spring multiple times in our procedure. So we're going to use the average value there. And then we're going to use the average velocity that corresponded to that compression when the ball comes out. And then we're going to calculate what the spring constant should be in newtons per meter. This would be meter per second. All right, so here's our table right here. So you're gonna say this is how you would do it. You don't actually have to do it, but you're going to describe how to do it. So you're going to using the average compression for position A for those multiple trials, we calculate what the velocity is. Using our equation for spring constant, we calculate what that spring constant would be for those variables. And then we do the same thing for position B and for position C. Use the average compression, the average velocity upon being launched, and then using our equation for the spring constant. And here, the answer we're looking for is if these K values remain constant as the X values change, then we know that the spring constant remains constant regardless of compression. And there's one other really cool way you could have done this. You could have answered question C graphically, because in physics, a common way to analyze data is to see if the data collected can be graphed in a linear way. So the equation of a straight line is y equals mx plus b. We can take this equation that we derived and make it fit the equation of a straight line. So taking this equation, I'm gonna put velocity squared on the y. So v squared is going to be on the y, which means x on the x-axis is going to be x squared. And then this is going to be k over m. So all I did here is I took this equation and I solved it for v squared. If you solve this for v squared, you're going to get k over m times x squared. And this fits the equation of a straight line. On the y-axis, we're going to put v squared. On the x-axis, we're going to put x squared. The slope should be k over m. Y-intercept should be 0, right? Because if x is 0, that means we didn't compress the spring, which means there's no velocity. So v squared, x squared, we would look for this. If we get a straight line, if the data points that we get from plotting v squared and x squared are a straight line, well, the slope of this should be k over m, and m is a constant. So if the slope is constant, that means that k is constant. Okay, very last question, and then we're done. Okay, very last question. Another student uses the launcher to consecutively launch several spheres with different masses. So now we're changing the mass of the spheres. Each sphere is launched from position A. So here's our launcher. So every single time, so we have these different spheres, right? And the mass of these spheres are different. They go into the launcher, but every time we're compressing the spring the same amount. And then the student creates a graph of launch speed versus sphere mass. What would this graph look like? Well, again, okay, we start out with potential of spring. When the sphere leaves the launcher, it's kinetic. Potential of spring equals kinetic. 1/2 kx squared equals 1/2 mv squared. 1/2s drop out, and we are now solving for, what are we doing here? We're solving, let's solve this for v squared. So solving this for v squared, we're going to get k over m times x squared. So here is the relationship. The thing to point out, in fact, let's just take this one step further, solve for v. This is going to be x, so we square root both sides. This is going to be x, k over m. The thing to recognize here is that mass is in the denominator. Yes, it's inside a square root, but bottom line is, whenever a variable is in the denominator, as this mass gets bigger, that's going to make velocity smaller, right? So bigger mass, as mass gets bigger, the launch speed, which is the velocity, is going to get smaller. So we're looking at something like this.